All right. Hey, everyone. How's it going? Hope your summer's going well. I've been really impressed by how many of you have already watched the videos for 1.1 through 1.3, subscribed to my YouTube channel, reached out with questions. You seem like a very self-motivated group, which is great. So keep that up. I know it's hard to do academic work in the summer. It's hard to be in the mood for that. But it seems like you guys are a good group of motivated students. Like I always tell my AP students, I can get you to a 3, which means if you do what I tell you to do in AP chemistry, I can get your score up to a 3. You'll get a 3, okay? But you can, from there, get yourself to a 5. So many of my students in the past have scored 5s on the AP chemistry exam, but every single one of them had self-motivation. So in addition to doing what I told them to do, they went above and beyond and got themselves to a 5. So keep that in mind as we work our way through. Also, and I told some of you guys this when you emailed me, this is just an overview of 1.1 to 1.5. We will be doing more notes, more practice problems on these topics when you get to school, okay? So think of these as like overview preliminary notes. We will do more notes and more practice problems once the school year starts, okay? All right, so for 1.4, this is going to be about mixtures, okay? If you think back to 1.2, 1.2 was all about elements, okay? Well, let me back up, okay? Write this down on the top of your worksheet. Matter. Chemistry is the study of matter. Matter is anything that has mass and takes up space, okay? Whether it's a solid, liquid, or gas. Matter can be divided into kind of 3 categories. There's things that are elements. These are on the periodic table. So pure elements are things like magnesium or a piece of iron or helium gas. Those are all elements. All the atoms are the same. All the atoms are the same. So if you have a piece of magnesium, all the atoms are magnesium. If you have a balloon filled with helium, all the atoms in there are helium. All the atoms are the same. So this is something like Mg, okay, for magnesium. Then we have compounds. Compounds are multiple elements bonded together in a fixed ratio, okay? So a compound is something like H2O, okay? 2 hydrogens bonded to 1 oxygen in a fixed ratio, okay? And that ratio doesn't change. You can't have water that's H3O or H4O or H2O2, that's not water, or H2O5. The ratio is always 2 to 1 for a compound, okay? And then the third type that we're talking about today is mixtures. Okay, mixtures are things that have different compounds and or elements mixed together. The air is a good example of a mixture. The air is mostly nitrogen gas. It's not mostly oxygen. A lot of people think the air is mostly oxygen. Air is mostly nitrogen gas, and nitrogen is diatomic, which means it exists in molecules of 2. Okay, you'll never see a nitrogen atom by itself. It'll always find another nitrogen to pair up with. So air is mostly molecules of N2. About 70-something%. That is mixed with oxygen gas, which is also diatomic. Oxygen comes in molecules of 2, O2, okay? That's why in biology, whenever you used oxygen in a chemical equation, like a photosynthesis or cellular respiration, it always had a 2 after it when it was by itself, because it's diatomic. If it's alone, those oxygen atoms will find another oxygen to pair up with and make molecules of O2. When it's in a compound, it doesn't always have a 2 after it. Please don't think, well, oxygen's diatomic, let me put a 2 here. No. It's just when it's alone, it always has a 2 after it. So that's the air is like 70-something% nitrogen, 20-something% oxygen. There's a little bit of carbon dioxide in the air, CO2. Not very much. Problem with the CO2 that's in the air is it's a greenhouse gas. It traps heat. So even with a very small amount of CO2 in the air, it can cause the greenhouse effect, which means when this starts to build up in the atmosphere, that the Earth starts to heat up. So the air on Earth is a mixture, mostly of these 3 compounds mixed together. So with a mixture, you always see a plus sign. That means mixed with, okay? This is not a fixed ratio, okay? In general, the air is 70-something% nitrogen, 20-something% oxygen, less than 1% CO2. But like I said, The CO2 is building up in the atmosphere. CO2 is a product of burning. Whenever we burn something, whether we're burning gasoline or other fossil fuels, this is building up in the atmosphere, okay? So because the air on Earth is not a fixed ratio of, it's not a fixed composition the way a compound is. A compound like water is always 2 to 1. The air is not like that. So this is starting the ratio of nitrogen to oxygen to carbon dioxide is changing. And the carbon dioxide part is starting to build up, which is causing climate change. So what we did back in 1.2 was we talked about elements, okay? And we learned about elements like magnesium. Even though if you have a piece of magnesium metal, all the atoms are magnesium, okay? They all have 12 protons, they all have 12 electrons. The number of neutrons changes. So we learned about, in a sample of magnesium, what's the composition of that, okay? So if you have a sample of magnesium, it's about 80% magnesium 24, 10% magnesium 25, and 10% magnesium 26. These are the mass numbers, right? So this one has 2 more neutrons than this one. So that varying number of neutrons is what changes the mass of magnesium. So we learn to look within an element and see what its composition is of isotopes of that element within the sample of the element. In 1.3, we learned about compounds, okay? So in 1.3, we learned about how compounds have this fixed ratio, okay? So if a compound is C2H6, that's a fixed ratio of 2 to 6, or you could say the empirical ratio would be 1 to 3. A ratio of 2 to 6, if you reduce it down, is 1 to 3. So we took the grams of each element in a compound, converted it to moles, because moles tells us how many, and then looked at that numerical ratio of like 7 to 7 to 1 to 2, okay? So in this one, we didn't analyze the composition of an element. We analyzed the elements that compose a compound. Okay, so we looked at a compound and what's the composition of the different elements in that compound. Okay, what we're doing in 1.4 is the components of a mixture. And this is a little trickier because the composition of a mixture can change. Salt water is an example of a mixture. It's salt, NaCl, dissolved in water, H2O, okay? You can have salt water with very little salt compared to water, or a very high amount of ratio of salt to water. So mixtures have a changeable composition, whereas compounds have a fixed composition, okay? So a mixture is when 2 or more pure substances, which means elements or compounds, these are considered pure substances. This is not, okay? So when you have 2 or more elements or compounds combined into a mixture, that's what makes a mixture. The mixture can be analyzed in order to determine the mass composition of each substance in that mixture. So just like we could take a compound and analyze the masses of all the things in the compound, we can take a mixture and analyze all the components of that mixture, okay? One thing we are going to be using in 1.4 is stoichiometry, okay? Stoichiometry is a type of dimensional analysis that you hopefully learned about in regular chemistry. If not, watch a video on stoichiometry. First, watch a video on dimensional analysis. That's what we did back in 1.1. Dimensional analysis is a way of converting units by multiplying fractions. So watch a video on dimensional analysis. Be sure you understand that. And then watch a video on stoichiometry. Okay, stoichiometry is a particular type of dimensional analysis that involves a mole ratio, okay, from a chemical equation. So it's a specific type of this type of thing, okay? So if you are not familiar with stoichiometry, or if you forgot a lot of stoichiometry, just pause the video, do a quick search on YouTube, watch a video on stoichiometry. It'll probably ring some bells and bring back memories from chemistry. So please do that before you watch the rest of this video. All right, and then what we have here is kind of a flow chart for stoichiometry. Stoichiometry, we use molar masses from the periodic table. So we learned about molar mass in 1.1. Molar mass is the grams per mole, okay? It's not grams, that's mass. It's the grams per mole is molar mass. So if you look back here, some examples of molar mass were like this factor right here, 1 mole for every 114.13 grams. This is a molar mass, okay? And this 114.13 comes from the periodic table, okay? This is not a molar mass because this is molecules per mole. Molar mass is grams per mole. And this is just a mass. This is just grams. That's a mass. Molar mass is the ratio grams per 1 mole. Okay? This is a molar mass written a different way, 18.02 grams per mole. That's 18.02 grams for every 1 mole. Okay? So this can be written like this or like this. These are both molar masses. Okay? So we're going to be using a molar mass. Then we'll use something called a mole ratio, and then we'll use molar mass again. That's how stoichiometry works, okay? Once we do the stoichiometry, we're going to be using that to figure out something called mass percentage of substance in a mixture, okay? Percent is always the same formula. It's the part divided by the whole times 100, okay? All the rest of this stuff you can kind of ignore. I did not write these notes, okay? When we get to school, the notes I give you will be ones I wrote. But these, you can read over it. I don't think it's that helpful at this point. Okay. Unfortunately for 1.4, the practice problem did not, because this is 1.5, the practice problem did not photocopy onto here. So on a separate piece of notebook paper, just write 1.4 practice, and we're going to do one practice problem. Again, this is just a preview of what we're going to be doing in 1.4. Don't worry too much, okay? So I want you to copy down this practice problem onto your own paper, okay? A 15.0 gram sample of sodium hydrogen carbonate, NaHCO3. This is how it'll be on the AP exam. They will give you the formulas, okay? Even though in chemistry we spend a lot of time learning how to take a name and write a formula, they will not be testing that on the AP exam. They will give you the formulas that go with the names. So that makes it a little too easy, I think, but whatever. When I took AP chemistry, went back in the 90s, they would not give us that. We would have to figure out which of these was sodium hydrogen carbonate, but now they give it to you. So a sample of sodium hydrogen carbonate, NaHCO3, that's baking soda. Just FYI, sodium hydrogen carbonate is baking soda, okay? Was contaminated with an impurity, okay? So that means this 15 grams was not all sodium hydrogen carbonate. There was other stuff mixed in with it. In order to determine the purity of the sample, which means how much of this was actually sodium hydrogen carbonate, it was heated to decompose the material according to the following reaction. So here you can see we have a decomposition reaction, where a decomposition reaction only has one reactant, and it breaks apart into multiple products, okay? So if you heat up sodium hydrogen carbonate, if you had me for chemistry, we actually did this in the lab. We put sodium hydrogen carbonate, baking soda, on the hot plate, and it decomposed, okay? It produces sodium carbonate, Na2CO3. This is also a solid. Keep in mind ionic compounds that have a metal, like Na, and nonmetals, like CNO, are pretty much always solid at room temperature, or even warm temperatures. Like we were doing this on the hot plate. This was a solid, this was a solid. Ionic compounds are solids, pretty much always, unless they are on the surface of the sun. That would be hot enough to melt them. They have to be really hot to become liquids. So usually in lab settings, even on a Bunsen burner or on a hot plate, ionic compounds that are metals bonded to nonmetals are going to be solids. The only exception is when they're dissolved, in which case they're dissolved in water, and we would say that they're aqueous, because ionic compounds usually dissolve in water. But if it's not dissolved in water, it's going to be a solid. So we took the baking soda, we heated it up, it produced sodium carbonate, which is also a solid. H2O, water, we think of that as normally a liquid. It's pretty easy to vaporize water here on Earth. You just have to heat it up a little bit. So when we do this in the lab, the hot plate is hot enough that the water is water vapor, which we say it's H2O gas, okay? So this is a solid. This is a solid. The H2O is going to be a gas. It goes off into the air. And carbon dioxide, as you know, is a gas, okay? So what we noticed in the lab was that the problem was both of these are white solids. Sodium carbonate looks exactly like sodium hydrogen carbonate. It's a white solid. So they look the same, but we know a reaction happened because this got lighter weight. This weighed less than this because some of the mass went off into the air as water vapor and carbon dioxide. So if 6.35 grams of sodium carbonate were recovered, what percentage by mass of the sample was sodium hydrogen carbonate, NaHCO3. So essentially we took this 15 grams of stuff, heated it up, and we're able to figure out the mass of this product that we made, the Na2CO3. So we're going to work our way backwards, okay? We know we made 6.35 grams of this. We're going to use stoichiometry to figure out, well, if we made 6.35 grams of this, how many grams of this did we have to begin with, okay? Keep in mind, if this is 6.35, we know that the mass of the reactant is going to be heavier than that because we can see some of the mass was released as gases, okay? So expect to get an answer that is higher than 6.35 for this mass, but we also need to be sure, we should expect to get an answer that is less than 15, okay? We had 15 grams of stuff, some of which was impurities, some of which was actual sodium hydrogen carbonate, so we should have less than 15 grams, but it should be bigger than the grams of sodium carbonate, okay? So feel free to pause the video and finish copying this down, okay? Be sure you watch a video on stoichiometry if stoichiometry does not feel very familiar to you, and then come back to this video, okay? So we are gonna use stoichiometry, and if you guys, I should have said this earlier, turn your paper sideways. That's why my paper's turned sideways, but I didn't mention it. Just because stoichiometry can like run off the page. So either turn your paper sideways or keep your paper upright and write real small, okay? So we're going to use stoichiometry. Okay, stoichiometry is when we take the mass of one thing, in this case we know the mass of Na2CO3, to figure out the mass of another thing in a chemical equation. So if you're doing stoichiometry, you'll always have a chemical equation to look at. So essentially the flow chart, which you see right here, I want us to copy this down again, okay? I'm going to write it slightly different. You're always going to start with the grams of A, okay? A means whatever the question gives you. In this case, A is Na2CO3. And you're going to convert that to moles of A. Okay, and to convert from grams to moles, we're going to use the molar mass. Okay, so that's what we did back in 1.1. Okay, if you look at the bottom of 1.1, this we had grams and we converted to moles. We did some other stuff later on, but essentially we're just doing this first step, getting grams into moles using the molar mass. Okay. A good rule of thumb for AP Chemistry is whenever you don't know what to do, convert to moles. Okay, if you ever don't know what to do, convert to moles, and sometimes you can kind of take it from there. If you look back at 1.1, the first thing we did with this grams was convert to moles. Then once we were in moles, we could go to molecules, okay, using like this flow chart, okay. If you look back at 1.3, okay, the first thing we did with all these grams was convert to moles. Once we were in moles, we could, tease out a numerical ratio, okay. Same thing here. If you don't know what to do, convert to moles, okay? Once you're in moles, you're going to use the mole ratio, which I will explain in a second, to get to what I say moles of B. Moles of B is the thing the question's asking you to find, okay? A is the substance that they gave you information about. B is the substance they want you to find, okay? The sodium hydrogen carbonate. So we're starting with Na2CO3 and going to NaHCO3. Then you're going to use the molar mass again, but this time it's going to be the molar mass of B, not the molar mass of A, to get from moles to grams of B, okay? And we might have, let me see if we did this. Yes, in exercise 3 of 1.1, we did this for exercise 3 of 1.1. First we went from atoms to moles, and then we went from moles to grams, okay? So kind of ignore this stuff, moles to grams, using the molar mass, okay? Whenever you see grams and moles in the same ratio, that's the molar mass. So we'll use the molar mass once again, but it'll be molar mass for B, not for A. So that's kind of our stoichiometry flow chart, okay? So we're going to start out with the grams that they gave us, okay? They gave us the grams of sodium carbonate, okay? You might be thinking, oh no, they gave us the grams of sodium hydrogen carbonate. No, they didn't. That was contaminated, okay? We did not have 15 grams of sodium hydrogen carbonate. But whatever process they did, they were able to figure out after they heated it up. They know for sure 6.35 grams of Na2CO3. Okay, put that over 1. This is the mass. It's the grams of something, okay? Put your time sign in a line. Leave some space for a number. Throw grams of Na2CO3 under the bus. Okay, whatever's here goes down here, so it'll cancel. And then the units that are in the circles are the units that go on top of every factor, okay? So we had grams of Na2CO3, that's A. Now we're going to do moles Na2CO3, okay, because that's also A. So we did grams of A on top of here, moles of A on top of here, okay? Then moles of B is going to go on the top of here, okay? B is the thing that we're trying to get to, okay? The question wants to know about sodium hydrogen carbonate. So we're trying to get to moles of NaHCO3. That's B, okay? Notice I'm leaving a spot for a number. Don't try to put any numbers. Put your units first. Don't say, Ms. Turk, where does the 1 go? I don't know where the 1 goes. I don't know where anything goes until I see a unit on the top and the bottom, okay? The unit on top matches what's in the circle. The unit on the bottom is whatever needs to be canceled out. Whatever was here, throw it under the bus here. Whatever was here, throw it under the bus here. Okay? And then for the top of the final factor, it's grams of B. So grams of NaHCO3. And then whatever's here gets thrown under the bus. Moles NaHCO3. Okay? So just to make things painfully clear, I'm just going to highlight. You don't have to do this on your own paper. Okay, so A in this case is what the question gave us. Okay, it's the Na2CO3. All right, so that goes here and here. Na2CO3, 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 and then it got thrown under the bus here. So we had grams of Na2CO3, grams of Na2CO3, moles of Na2CO3, moles of Na2CO3. Okay, and then B, I'm going to highlight with orange. B is what the question's asking about, which in this case is NaHCO3. Okay, so that goes on the top of this factor, the top of this factor, and it gets thrown under the bus here. Okay, so that's kind of our stoichiometry setup, okay? Now let's try to fill in our numbers, okay? Whenever you see grams per mole, whether it's flipped this way or flipped this way, these are molar masses. They come from the periodic table, okay? So this is not the molar mass. This is the mass. This is the grams. It is not the grams per mole, okay? Just like, let's say I'm driving at 50 miles an hour. Let's say I go 25 miles at a speed of 50 miles per hour, okay? The 25 miles is the miles I traveled, okay? Whereas the 50 miles per hour is the rate at which I traveled, okay? The miles per hour is a relationship. It's a compound unit like this here. Whereas this is just a simple unit. It's just grams. Okay, so remember, molar mass is on the periodic table, okay? So we're going to add up the mass of 2 NAs, 1 C, and 3 O's. So NA's right here, so we'll do 22.99 times 2 plus C, which is 12.01, plus 3 times the mass of oxygen, which is 16. You get 105.99. That's the molar mass. You got to think to yourself, is molar mass the moles per gram or the grams per mole? Molar mass is grams per mole. So this number goes where grams is, okay? 105.99 grams per 1 mole, okay? Grams per mole means grams per 1 mole, or the grams for every 1 mole, all right? This right here is not the molar mass, okay? This is what we call the mole ratio. And the thing that makes stoichiometry different from just run-of-the-mill dimensional analysis like we did in 1.1 is the presence of a mole ratio. That's how you know you're doing stoichiometry, a specific type of dimensional analysis. You'll see moles over moles somewhere in the setup. The mole ratio comes from the chemical equation. So stoichiometry will always involve some type of chemical equation. Remember, moles does not tell you how heavy, it tells you how many. So for moles, we look at the coefficients. The coefficients are the numbers in front, okay? That tells us how many. So for every 2 NaHCO3s, when there's no coefficient, it's a 1, we get 1 Na2CO3, 1 H2O, and 1 CO2. So the coefficients tell you how many. They don't tell you how heavy, because obviously these have very different masses. So they're not, in terms of mass, not a 1-to-1-to-1 ratio, but in terms of how many, they're a 1-to-1-to-1 ratio. So for every 2 molecules of NaHCO3, you'll get 1 molecule of Na2CO3, 1 molecule of H2O, and 1 molecule of CO2. Okay? We could scale that up. For every 2 dozen NaHCO3s, you'll get 1 dozen Na2CO3s, and 1 dozen and 1 dozen. Individual molecules, dozens of molecules, are not useful in the lab. That's why we scale up to a mole, okay? Because a mole of molecules is enough that we can actually see it. So scale it, instead of scaling up to dozen, we scale to a mole. For every 2 moles of this, we get 1 mole of this, 1 mole of this, 1 mole of this. It tells us how many, okay? So it's essentially a 2-to-1 mole ratio. For every 2 moles of NaHCO3, because that's its coefficient, we get 1 mole of Na2CO3, because that's its coefficient, okay? So the mole ratio, you look at the coefficients for each substance, okay? Be sure you have your units written out before you try to figure out the numbers. Without this written down, I don't know what coefficients to look at. Write down all of this, then fill in the numbers, all right? And then the last factor is the molar mass, okay? This time it's the molar mass of NaHCO3. So take your periodic table, NaHCO3. So Na is 22.99 plus 1.008, because that's H, plus 12.01, plus oxygen is 16 times 3, because there's 3 oxygens in that formula, and you get 84. We're going to round that to 84.01. Okay, always round your molar masses from the periodic table to 2 digits after the decimal. So once again, molar mass is the grams per mole, not the moles per gram. Molar mass always goes, this number goes where grams is, which here happens to be on the top. Here it was on the bottom. Okay, so it's the grams per 1 mole. Okay, so cancel grams of Na2CO3, grams of Na2CO3. Moles Na2CO3, moles Na2CO3. Moles NaHCO3, moles NaHCO3. And we'll multiply straight across the top. When you multiply fractions, you go straight across the top. 6.35 times 2 times 84.01. Okay? Then do divided by, and it'll take your previous answer. Press divided by. Open your parentheses. Actually, the only thing on the bottom is the 105.99. Okay? And we're just going to round that to 10.1 grams NaHCO3. Okay, and just double check and be sure your answer makes sense. You can't always do this with stoichiometry, but in this type of thing you can. We knew it was going to be heavier than 6.35 grams, which it is. And we knew it needed to be less than 15 grams, because if our substance with impurities was 15 grams, then the stuff, the pure stuff would have to be a part of that. Okay, so our answer is definitely in the range that makes sense. And then to figure out the percent by mass of the original sample that was the sodium hydrogen carbonate, we're just going to use our percent formula, which is part divided by whole times 100. So the part that was the NaHCO3 was 10.1 grams. The mass of the whole thing was 15 grams. Cancel grams, okay, and do 10.1 divided by 15. Oops, I forgot. And then you multiply by 100. Okay, so anytime you're doing a percent, you do the part divided by the whole times 100, and you get 67.3%. Okay, and you can kind of tell that's about 2/3. About 2/3 of the 15 gram sample of stuff was the pure stuff. Okay, it's helpful when you see something that has impurities to call it stuff. Okay, like above the 15 grams, this is stuff. Okay, It's not pure sodium hydrogen carbonate. There's a lot of impurities mixed in. Okay. All right, so that's the only practice problem we're going to do for 1.4. Again, if you feel rusty on the stoichiometry, definitely watch videos on YouTube. Stoichiometry is a very common chemistry skill, so there's lots of videos out there. Do some practice problems and get comfortable with it. All right, so that's it for 1.4.